Okay, I want you to close your eyes for a second.
Mhm.
Just imagine you're standing with me on Mars, on this high plateau, Valais Marineris.
Right.
The first thing you feel is the cold. It's this brutal, dry cold, maybe minus 90 degrees Celsius.
So bone-chillingly cold.
Exactly. But the sun above you feels like a laser. The atmosphere is so thin, there's nothing to filter it. And the ground under your feet isn't sand. It's this fine, red dust regolith that gets into everything.
And that dust isn't just, annoying. It's chemically aggressive. We're talking about perchlorates.
Yeah, the stuff we use here on Earth as like an industrial bleaching agent.
So it's not just an inconvenient place. This is an environment that is actively, physically trying to take you apart. And any machine you bring with you.
It is fundamentally trying to kill you. And the very first thing you need to survive out there, whether you're on the moon or on Mars, is a roof, a thick, solid roof.
You need heavy protection. Not just for the temperature, but from the radiation.
Oh, the radiation is the big one, because that thin atmosphere means you're getting hit with, what, up to 700 times the dose you'd get on Earth?
That's the prediction.
Yeah.
And a shield against that kind of radiation can't be flimsy. It needs mass. We're talking tons and tons of material, maybe meters thick, just to keep the crews safe long term.
So that's the mystery, right? That's the fundamental problem of us going out there to stay. How do you get literal tons of building material millions of miles from Earth?
You can't. Not with our current model. We've always just packed everything you need with us.
We take it with us. But now we're talking about building a city. And the answer, the thing that's really shaking up the whole space community, is that the architects of these first Martian cities, they won't be robots.
No.
They're going to be the smallest, oldest life forms on our planet. Microbes, bugs that have been literally shaping Earth's geology for billions of years.
It's a complete revolution in strategy. We're moving away from a take strategy, where you haul everything with you, to a make strategy.
You make it where you land.
Exactly. You use these little biological factories to build what you need right there.
And that is our deep dive for today. We're going to explore this wild idea that the future of space exploration hinges on using microscopic bugs to turn toxic dust and, yes, human waste into habitats, food, and medicine. Microbes as the architects of our future off-world.
This is going to be a weird one. I love it.
All right, let's get into the main antagonist of this story. The insane cost of just getting stuff into space. Why is launching even a single kilogram such a villain?
It's pure physics, really. You're trying to escape Earth's gravity well, which is enormous, and you have to do it with, controlled explosions. It's brute force.
And the price tag is just, it's mind-boggling. To get 1 kilogram, like the weight of a laptop into space, you're looking at anywhere from, what, $2,700?
That's on the absolute low end for, low Earth orbit. If you want to go to deep space, it could be $54,000 for 1 kilogram.
Wait, $54,000
Yeah.
for a laptop's worth of weight.
Yeah. It's sticker shock. But it's more than just the money. It's about the mass budget. Every mission has a weight limit. If you spend that budget on, say, a bunch of metal beams or concrete blocks,
Then you can't bring spare parts. Or extra food. Or critical medical supplies.
exactly, you're making a trade-off with every gram.
Okay, let's put that into real terms. Say we have a 6-person crew going to Mars. The trip is roughly 3 years, round trip. That's the current plan.
And that crew has to eat.
They have to eat. And the food alone, just the food for those 6 people, is over 10,000 kilograms. 10 metric tons.
And that's with, super optimized dehydrated rations. That's not gourmet meals. That's just survival calories.
Right, and that's before the habitat, the power systems, the water recyclers, the oxygen, all of it. So if we already have to ship 10 tons of food, shipping another 10 tons of bricks is...
It's a non-starter. The source material is very blunt about that. You just can't do it.
This is why missions beyond low Earth orbit change the game. On the International Space Station, you can get a resupply mission in a matter of days.
But for Mars, just-in-time delivery is months, maybe years away. That supply chain just doesn't exist.
So you have to flip the whole model on its head. Instead of taking supplies, you have to generate them there. Which brings us to 2 really important ideas. The first is ISRU, In-Situ Resource Utilization.
Right. I like to think of ISRU like you're an old-school pioneer heading out west.
Oh.
You don't pack up your entire pre-built cabin and haul it with you on the wagon. That's insane. You bring the tools, the axe, the saw, and when you find a good spot, you start chopping down the local trees to build your house.
So in space, the local trees are the Martian dirt, the CO2 in the atmosphere, maybe some water ice.
Exactly.
Yeah.
You harvest what's there. The second concept, which is maybe even more important for a long trip, is loop closure. LC.
Loop closure.
This is basically radical efficiency. If ISRU is about using the planet, loop closure is about using everything else over and over and over again.
Okay, give me an analogy for that one.
Imagine a perfectly closed loop kitchen. Every single scrap of food, every drop of water from the sink, even the steam from the pots, it all gets captured and put back into the system to make your next meal.
Nothing is wasted.
Nothing.
Yeah.
You can't afford waste. Every piece of trash is mass that you paid a fortune to launch from Earth, and you can't replace it. So waste has to become a resource.
But it's not just a logistics problem. The planet itself, Mars, is just, it's uniquely awful for building things and for life.
The planetary stressors.
Yeah.
They're intense. We talked about the temperature swings down to minus 90 C. That kind of thermal cycle will just tear conventional materials apart over time.
Yeah.
Concrete would crack, seals would fail.
And the dirt, the regolith itself, you said it was toxic because of the perchlorates, but it's also physically mean, isn't it?
It is, yeah. It's incredibly abrasive. This isn't like soft beach sand that's been worn down by water for millions of years.
Right.
It's been formed by micrometeorite impacts and thermal stress in a vacuum. So the grains are sharp, they're jagged, like tiny shards of glass.
Which would just shred seals, clog up moving parts in your equipment, get everywhere.
It's a mechanical nightmare, but it's also a biological one for the little microbes we want to use as our factories.
How so?
Well, on top of the perchlorates, the regolith is full of metal ions, lots of iron, lots of magnesium. And those metals just naturally act as antimicrobials.
Wait, so the very ground we want to use as a building material is also a poison that's trying to kill the builders?
Exactly. It's
Yeah.
chemically aggressive and toxic at the same time. It's trying to kill the microbes we bring and then break down whatever structures they manage to create.
Okay, so let's sum this up. Conventional construction is out because it's too heavy and expensive, and the local material is this loose, sharp, toxic dust. We need a way to bind it all together into something strong without tons of water or heavy machinery.
That's the challenge. And the answer is you have to think small, really, really small.
Which brings us to this whole philosophy of bio-inspired solutions. If the problem is that big and brutal, the solution has to be tiny and smart.
And self-replicating. That's the key. There's this great quote from a NASA scientist basically saying, you look at a problem like turning sand into stone,
Yeah.
and you realize biology already solved that problem billions of years ago. You just have to find the bug that did it and, convince it to work on Mars.
That's such a great way to put it. We're not building a machine, we're programming a life form, using synthetic biology to turn a cell into a tiny factory.
And we're looking at Earth's earliest, toughest life forms for the blueprints. We're talking about biomineralization.
Biomineralization.
It's the process where microorganisms like bacteria, or the little polyps that build coral reefs, create mineral structures. It's a natural part of their metabolism. They're basically turning their soft bodies into rock and shell.
So the thinking is, if a microbe can build a massive coral reef that can withstand all the pressure and chemistry of the ocean,
maybe it can build a habitat wall that can withstand the vacuum of Mars. It's the heart of that make versus take strategy. You don't ship the final product, you ship the genetic recipe and let the bugs do the manufacturing on-site.
to get to that level of self-sufficiency, though, you need that perfect closed loop we talked about. And the European Space Agency, ESA, has been working on the gold standard for this since, 1989? A project called MELISSA?
Yeah, MELISSA.
Yeah.
It stands for Microecological Life Support System Alternative. It's this huge, long-term engineering project. But the inspiration behind it is actually pretty simple.
Which is?
It's basically modeled on a lake, a tiny, perfectly controlled, self-sustaining aquatic ecosystem. But for safety and engineering, they broke it down into compartments, like a factory assembly line.
An assembly line that takes waste from the astronauts and turns it back into things they need.
Exactly. Let's walk the factory floor.
Yeah.
So the input is the crew. They're producing waste and edible parts of plants, human waste, and they're exhaling CO2. All of that goes into compartment 1.
Okay, what's in compartment 1?
That's the breakdown crew. It's full of special anaerobic bacteria, bugs that love heat and have no oxygen. Their only job is to start liquefying and decomposing all that complex organic gunk into much simpler molecules.
Yeah, what?
Mostly things called volatile fatty acids, VFAs, and ammonia.
Got it. Then the VFAs go to compartment 2, and the ammonia moves down the line to compartment 3.
Right. And compartment 3 is the cleanup crew. It has nitrifying bacteria that take that ammonia, which is toxic, and convert it into nitrates, which are basically plant food. It's a detoxification and food prep step, all in one.
And then all of these processed, clean nutrients, plus the water and the CO2 from the crew, flow into the final compartment, compartment 4.
which is the heart of the whole system.
Yeah.
Compartment 4 is where the magic happens. It's full of photosynthetic life, either cyanobacteria like spirulina or actual higher plants like wheat or potatoes.
And that's what produces the final outputs for the crew.
Yep, fresh food, breathable oxygen, and clean, purified water. It's this beautiful, elegant circular design.
But the sources we looked at were pretty clear that even after decades of work on this, it's still a massive engineering challenge. What's the main bottleneck in this perpetual motion machine?
The waste. Specifically, breaking down the organic waste in that first compartment is the real sticking point.
Oh, so.
Well, when they first ran the pilot system, they only got about 70% efficiency in breaking down all the organic matter and recycling the nitrogen.
Wait, hold on. 70% sounds pretty good for a first try. Why is that a deal breaker?
Because in a closed loop that has to run for 3 years, that other 30% that doesn't get broken down, it starts to build up. Think of it like a filter in your house that you never clean. It just gets more and more clogged. That 30% is made of really tough, fibrous stuff like cellulose from the inedible parts of plants. And bacteria have a really hard time breaking that down quickly.
So you get this buildup of like stubborn sludge that's locking up all these valuable nutrients like nitrogen that are supposed to be going back into the food chain.
Precisely. And to get the efficiency over 90%, which is what you need for a truly long mission, they had to add in other more high-tech systems, like high-pressure, high-temperature cookers, basically, to just blast those tough fibers apart.
So the biology is amazing, but it still needs a heavy-duty engineering backup just to handle the leftovers.
The biology gets you most of the way there. The engineering has to finish the job.
Okay, so waste recycling is tough, but what about the other stuff we need to make on demand? Like nutrients and medicine. You can't just pack a 3-year supply of vitamins. They degrade.
And this is where that on-demand biomanufacturing idea really shines. There's a NASA project called Bionutrients that's a perfect example. They're engineering yeast.
Like regular baker's yeast.
Same family, yeah.
Yeah.
But they're using gene editing tools like CRISPR-Cas9 to give it new instructions.
CRISPR is like a find and replace tool for DNA, right?
That's a great way to put it. And they're editing the yeast to produce specific vital nutrients that break down really quickly in storage. Things like beta-carotene and zeaxanthin, which are powerful antioxidants.
So instead of packing a vitamin pill that's useless after 2 years, you just pack a little dehydrated packet of this special yeast.
Exactly. The astronaut just adds some sterile water, lets it incubate for a bit, like making yogurt, and then freezes it to stop the process. And boom, you have a fresh supply of essential nutrients.
It's actually kind of low-tech in a way. It's based on fermentation, a process humans have been using for thousands of years.
That's the genius of it. It's reliable. And it's not just for food. They're doing the same thing for medicine. Another project engineered cyanobacteria, that blue-green algae, spirulina, to be a real workhorse.
You said that's the stuff in the MELISSA system making oxygen, right?
Yep, it's already taking CO2 and making oxygen. But they found that by adding just 2 extra genes, they could get the spirulina to also synthesize the active ingredient in paracetamol.
You mean like Tylenol, a painkiller?
The very same. So the organism that's making your air and can be used as a food source is now also making your medicine.
That is the definition of a Swiss Army knife organism. Air, food, and medicine from one bug. But we keep coming back to the environment. We need bugs that can do all this while getting blasted with radiation and poisoned by the soil.
Which leads us to the hunt for extremophiles, organisms that already love living in hellish conditions here on Earth.
Where are they even looking for these things?
All the craziest places you can imagine. They're studying fungi that were found growing inside the walls of the Chernobyl reactor, literally eating radiation.
No way.
They're looking at microalgae that thrive on Antarctic snowfields with constant UV and freezing temperatures. They're even finding bacteria here on Earth that have evolved to live in perchlorate-rich soil.
So they're collecting all these genetic superpowers from nature's toughest creatures. How do you get all of that into one super microbe for Mars?
The main technique is called directed evolution. It's basically evolution on fast forward.
You're not waiting millions of years for nature to do it.
Exactly. You do it in the lab in a few months. You introduce some genetic changes, create thousands of slightly different versions of your microbe, and then you hit them all with a simulated Martian environment. The cold, the dryness, the toxins, all of it.
And you just see which ones survive.
And not just survive, but which ones still do the job you want them to do, like produce that nutrient or that polymer. You select the winners and you repeat the process. You're steering their evolution towards a very specific goal.
And the beauty is once you've designed that perfect, resilient microbe, that's all you have to ship. Not the medicine, not the food, not the bricks, just the bug.
You ship the design plan, the biological code,
Yeah.
and you let it get to work on site.
Okay, so we've got life support, food, medicine, but we still haven't solved that first massive problem, the radiation shield. We have to stop launching bricks.
Right. The number one goal is to take that loose red dust and somehow turn it into a solid structural material, using only what's available. And the answer is biological mortar.
How on earth does a tiny soft microbe create something as hard as stone?
It's that process we mentioned earlier, biocementation. Specifically, something called microbially induced calcium carbonate precipitation, or MICP for short.
MICP, okay. And calcium carbonate is the same stuff in seashells and coral reefs.
It is. The bacteria are basically acting as millions of tiny, decentralized cement mixers. They glue the grains of regolith together from the inside out.
How? What are they actually doing?
It all comes down to their waste product, believe it or not.
Their waste is cement. That's amazing.
It's all about changing the local chemistry. The key reaction is called ureolysis. The bacteria are really good at breaking down urea.
Urea, which is found in?
Yep. And when they break it down, it makes the immediate environment around them much more alkaline. It raises the pH.
And why does that help make cement?
Okay, think about the hard water scale you get in a kettle or on your shower head.
Yeah, that white, crusty stuff.
That's calcium carbonate. The water has dissolved calcium in it. When you heat the water, you change the chemistry, and it can't hold on to that dissolved mineral anymore. So it solidifies, it precipitates out of scale.
Ah, okay, I get it. So the bacteria are doing with chemistry what boiling water does with heat. They're making the water less able to hold the minerals, so the minerals turn into a solid.
Precisely. The higher pH forces the dissolved carbonate minerals to solidify. And if there are calcium ions around, boom, you get solid calcium carbonate. And it forms right on the surface of the bacteria themselves, which act as perfect little seeds, gluing all the nearby grains of dust together.
But to get this to work on Mars, the scientists knew they couldn't just use one type of bug. They needed a team, a partnership. Who are the stars of this construction crew?
So first you have the binder, the main worker, a bacterium called Sporosarcina pasteurii. This is the classic bug for this kind of work. It's the one that's really, really good at that ureolysis reaction we just talked about.
So it's the cement mixer.
It's the cement mixer. And then you have its partner, which is the shield, the survivor.
Okay.
And that's a cyanobacterium called Crucoxidiopsis. This thing is an extremophile. It's known to be able to handle simulated Mars conditions. And its job is twofold.
What does it do for the cement mixer?
First, Sporosarcina pasteurii needs oxygen to live, but the Martian atmosphere is 95% CO2.
Right, not helpful.
But Crucoxidiopsis is photosynthetic. It breathes in that CO2 and uses sunlight to produce oxygen for its partner right where it's needed. Second, it creates this gooey outer layer of extracellular stuff that acts like a biological sunblock. It shields both of them from the harsh UV radiation.
So one bug makes the glue, the other makes the oxygen and provides the sunblock. That's some serious teamwork, but hang on, isn't that a huge risk? Relying on a living two-bug system for your house, what if something happens and the shield bug dies off? Does your house just fall apart?
That's the big question, right? It is a risk. But the whole point is that they are self-replicating. If a section gets damaged, you just give them the right conditions and they grow back. Compare that to a metal habitat wall. A micrometeorite hits it, you have a hole. That hole stays there until a human comes and patches it with material you had to ship from Earth.
Whereas with this, the builders are also the repair crew.
Exactly. The same microbes that built the wall can be used to heal any cracks that form. The risk comes with the reward of resilience.
Okay, that makes sense. Which brings us to the less glamorous but critical ingredient for this whole cement-making process, the urea.
The but important detail, yes. Astronaut urine.
I mean, it is a perfect example of a closed loop. You absolutely cannot afford to just throw away the nitrogen in urea.
Mission planners don't even see it as waste anymore. It's a chemical feedstock. It provides the urea to power the whole reaction, and it also contains other ions the microbes need to grow, like calcium and potassium.
So there it is, the complete kind of gross but totally sustainable circle of life on Mars. Humans make waste.
The microbes eat the waste and use it to turn the toxic dust into a solid.
And that solid becomes the habitat that protects the humans so they can keep making the waste.
It forces you to rethink what waste even is. The astronauts are no longer just consumers of resources. They are a biological input for the city's infrastructure.
Okay, this all sounds amazing in theory, but have they actually done it? Have they made real solid space bricks?
They absolutely have. They've done a bunch of experiments mixing this microbial slurry with simulated Mars and moon dirt. These simulants are designed to be as close to the real thing as possible, chemically and physically.
And what happened when they used the Mars simulant soil, the MSS?
They found it was actually pretty tough to work with, much harder than regular sand. They needed to add some performance boosters.
Why? What was the problem with the Mars dirt?
It comes back to those stressors we talked about. The Mars simulant is full of those inhibitory metals, lots of iron and magnesium. And those metals were messing with the key enzyme, the urease enzyme, that the bacteria use to make the cement. The dirt was actively fighting back.
It was stopping the glue from setting.
Basically, yeah. So they needed to add something to help the bacteria overcome that.
What did they use? Was it something you could actually take to Mars?
Yeah, two pretty simple low-mass things. First was gargum. It's a natural polymer, a common food additive. It just acts as a binder, kind of a natural glue to help hold things together.
Okay.
And the second was nickel chloride. Nickel is a key part of that urease enzyme's structure. So adding a little extra nickel supercharged the enzyme, helping it fight off the negative effects of the iron and magnesium.
And with those two additives, did they get a solid brick?
They did. The Mars bricks reached a maximum compressive strength of about 3.3 megapascals, or MPa.
All right, 3.3 MPa. What does that actually mean? Is that strong? Can it hold up a roof?
So, for context, a regular concrete sidewalk might be around 15 or 20 MPa, so it's not super concrete, but it's way, way stronger than just packed down dirt. It's comparable to a medium-strength clay brick you'd fire in a kiln.
So it's definitely structural.
It's structural enough to be used as, say, filler blocks, or as part of a layered shield where you just need bulk mass for radiation protection. And most importantly, it proved the mechanism works. You can make a solid object out of toxic Martian regolith using bacteria.
And what about the lunar simulant, the moon dirt?
That was actually easier. The lunar simulant was less chemically hostile. The urease enzyme worked better. Without any additives, they still got a solid brick. But when they did add the gargum and the nickel chloride,
It got even stronger.
much stronger. The lunar bricks hit an average of 5.65 MPa.
No way. So the moon brick is almost twice as strong as the Mars brick, just because the dirt is different.
Exactly. It shows that you can't have a one-size-fits-all solution. You have to tailor your biological toolkit to the local geology you find.
And this isn't just about building the initial base, it's also about maintenance. Things are going to break.
Right. And you can't ship a repair kit. So they tested MICP as a self-healing material. They took some pre-made lunar bricks and deliberately damaged them. Cut notches in them, drilled holes to simulate cracks from impacts or temperature stress.
They wounded the structure,
Yeah.
and did the microbes heal it?
They filled those cracks and holes with the microbial slurry and just let them do their thing for a few weeks. The results were pretty amazing. They saw a strength recovery of between 28 and 55%.
55%. So a crack that could have been a major failure is now more than half as strong as it was originally.
It proves the concept. The bacteria created a biological weld, bonding the new material to the old brick. It means your maintenance crew is a self-replicating liquid you can just inject into a wall. It's a huge step toward being independent from Earth.
So we have microbes making food, medicine, oxygen, bricks, and self-healing mortar. This is clearly way bigger than just construction. This is about using biology as a kind of everything tool.
That's the vision. Bio-in-situ manufacturing. And the different things these bugs can do is incredible. They're not just cement mixers. They can be miners too.
Biomining, yeah, that's critical. If you want to 3D print tools or electronics, you need pure metal. You can't ship that from Earth.
Nope. So researchers found a bacterium, Shigella wanadensis, that can do it. This bug is a specialist in moving electrons around, and it can process the iron oxides that are everywhere in the Martian dirt.
It turns rust back into usable metallic iron.
It essentially refines the ore for you. It's a biological metal worker, and it dramatically reduces the need for giant, power-hungry smelting plants.
And is the quality any good?
Surprisingly good. They took the iron powder produced by the bacteria and used it in a 3D printer. The resulting iron blocks were 4 times tougher than similar parts made with traditional methods.
That's amazing. Okay, from infrastructure to personal safety, radiation is the big silent killer. How can microbes help with that, beyond just building thick walls?
This is a really cool application. We're moving into diagnostics. Researchers are developing clothing, fabrics that are treated with special strains of bacteria.
You're talking about smart suits, biosuits.
Basically, yeah. These bacteria are engineered to change color when they're exposed to radiation.
So your suit is your dosimeter.
Exactly. It's a real-time visual warning system.
Yeah.
Instead of checking a little electronic device, you just glance at your sleeve. If the color has changed past a certain point, you know your accumulated dose is too high and you need to get to shelter immediately.
It's a constant, visible health check woven right into your clothes. So all these different breakthroughs, food, medicine, construction, mining, safety, they're all pointing towards one big idea.
The space Bio-Foundry. The ultimate goal, this would be a fully automated facility on the moon or Mars for engineering and analyzing biological systems.
How is that different from just having, the yeast packets and the spirulina tanks we already talked about?
It's about flexibility. The yeast packet can only make what it was programmed on Earth to make. The Bio-Foundry is like a biological 3D printer for molecules. You can digitally transmit a new genetic design from Earth for a new drug, a different kind of plastic, a stronger polymer for your bricks.
And the foundry builds it on site.
It prints the molecule you need on demand. So if some new unexpected medical issue comes up, Mission Control can just email the genetic code for the right drug and the crew can make it. It's incredible mission resilience.
This vision is so powerful, but the sources were clear. We're not there yet. What's the biggest scientific hurdle we still need to overcome?
The big one is what they call stacked stressors.
Stacked stressors.
Yeah, most of the experiments we've talked about test for one thing at a time. They'll test how a bug handles radiation or how it handles perchlorates or how it handles low temperature.
But on Mars, you get all of that, all at once, plus microgravity.
All at the same time. And we just don't know how these microbial teams will perform when they're getting hit with everything at once. Does the combination of stressors make things exponentially worse? We need to find out.
And what about the engineering challenges? Scaling this up from a lab bench to a full-size habitat has to be incredibly difficult.
The practical problems are huge, starting with the regolith itself. That abrasive dust is just a menace.
We said it was sharp. What does that do to the machines?
It just destroys them. It grinds down pumps and valves. It clogs the nozzles on the 3D printers. It gets into seals, which is a disaster in a pressurized building. You need incredibly robust, probably self-healing hardware just to handle the dirt.
And what about the biocementation process itself? You need the cement to form after you've printed the wall shape, not inside the printer?
That's a critical timing problem. If it hardens too early, it clogs the whole system. You need perfect control over the chemistry to make sure the reaction only kicks off so the slurry is in its final position.
And finally, gravity. Everything we know about how these things work is based on Earth's gravity.
And reduced gravity changes everything. How fluids move, how gases exchange in a bioreactor, how the bacterial biofilms grow and attach to surfaces. We can't just assume a system that works here will work there.
So we need to test all of this in partial gravity.
Desperately. Which is why the upcoming Artemis missions to the moon are so important. The moon is the perfect proving ground to test these biocementation and life support technologies before we commit to that long, multi-year journey to Mars.
Okay, so let's bring this all home. What's the big takeaway from this deep dive? It seems like the only way we survive for long periods off-planet is by letting biology solve the problems that our current engineering just can't.
It is. These microbial systems are the only way to truly close the loop. They take toxic dust and human waste and turn it into everything we need to live. The smallest forms of life are offering us the biggest solutions.
And what's really fascinating to me is that all of these systems, designed for the extreme resource scarcity of space, they're all built on total recycling, radical circularity.
And that's the connection back to us. The solutions we're designing for Mars, how to handle waste, how to build self-healing infrastructure, how to make everything from what's around you, those could be the blueprints for solving our own sustainability challenges right here on Earth.
So the ultimate measure of whether we can make it out there won't be how much we can build. It'll be how well we learn to recycle.